Hey guys, welcome back to the channel. I'm back with another exercise for you. This week we're going to do a cool parametric skateboard park, which is inspired by probably you've seen some of these iterations where you have kind of a landscape and you have kind of profiles that sweep around curves. So this is a really dynamic way of modeling NURB surfaces, and we're going to do a parametric iteration of it. So for this one, I used multiple circles that could be combined using a single polyline that we're going to compute using convex holes. And then we're going to do perpendicular frames and find these arch type of profiles, and we're going to sweep this profile at the end to get something like this. And this is a parametric object, so we're going to have a lot of options to customize, to rotate, to move this around, to scale it up or down, and there are going to be multiple ways of configuring this thing basically. So let's get right to it. We're going to build this from scratch. So I'm going to start with a point at the origin. So let's start at the origin, and I'm going to start with a circle actually. So we need the first 3 circles that are tangential to each other. So this could be at any radius value, but let's keep it rounded and we can move it up and down. And in the next phase, what I want to do is another curve that is tangent to this. So that one will have to be, let's say, we find another point on this curve and I want to place it somewhere here, right? So that's going to be we're going to use this vector from the center and we're going to displace it to the new center, and the new circle with the radius R1, let's say, is going to be tangential to the first initial circle. So we need to build that type of parametric relationship. So I'm going to first do evaluate curve. So we can evaluate any point around this circle, and I can use a simple number slider. And if you reparameterize this part, then you can actually go all around the circle and find a new point. Then we can do vector to point, and we can find the vector pointing from the origin to this evaluated point. And a vector is actually a direction that has a length or a magnitude as well. So if you want to see what this looks like, you can do vector display. And a vector display basically requires a vector and anchoring point. So you can use the origin as well. So you can see this is the vector that we created between these 2 points. So that represents the translation between the origin and this evaluated point. And if I evaluate some other point, it will direct in that direction. So I want to move this point that we have evaluated using this vector. But what I want to do is set its magnitude to be something else. So to do that, we can use vector amplitude. So vector amplitude basically will set the length or the magnitude of a vector to be something. So we can do, for instance, 2.5, and this is my amplitude. So if you want to view what this looks like, you can see that you can actually compute its length. So this could be our translation, and I can move this evaluated point using this vector, right? So you can see that the vector is being displayed from the origin, but if I move it to the evaluated point, that will be how much we want to move that point along the circle. So if I move the evaluation, it will move in any other direction that we want. Now this new point will be the center of a new circle. So I want to set another circle there, and this circle will have a radius that matches the amplitude of the new vector, right? So whatever magnitude I give, the new circle will always be tangential to the initial one. Now we have two circles, which is here the circle A that is located at the origin and the circle B, which is tangential to it. So I can actually create something else, which is tangent lines between two circles. So the tangent lines X, let's see where this is. It's under curve, primitive, and tangent lines X. So this will find, let's say, the tangential lines between these two circles. So wherever I evaluate, these tangential lines will move along with it. So, and then what I want to do is essentially place a third circle that is tangential to both of these, so that we get almost like a triangular base. So that one, we are actually going to compute some point here, and we want it to be the center of a new circle here. So essentially my goal is to find kind of a shape that is organic enough, that is made out of three circles, and then we're going to compute the sections that are formed around this circular shape as well. So that's kind of the trajectory I'm heading. Now that we have these tangential lines, we have two curves, and let's find out which one we might want to use. So we can also do point on curve, and we can, let's start with T1. T1 is here, so I can move any point along this curve. This is a bit different than evaluate curve. It would actually have given me the same thing. We could have actually used evaluate curve. It's essentially an evaluation that is normalized. So this basically takes in that the length of this curve is between 0 and 1, so we can actually evaluate any point of it. So 0.5 would be half of it. So now that we have this point, what I want to do is create a circle that uses two tangential curves. Create a circle tangent to two curves. Now the trick with this one is that it takes two curves for tangency, but then it requires a point, circle center point guide, and that is because we have two curves. It might be we have two curves, right? So if you think about it, without giving the point, the circle could be right here or it could be right here. These two are still tangential to each other, so you need to give a point that guides which direction you want the tangent circle to be placed. So for that reason, we need to evaluate a point here, and that also affects how the radius of the new circle is computed. So let's look at that quickly. So we have the circle that rests on the origin, we have the new circle that is tangential to it, and we have this guiding point. So this point somewhat acts like almost like the circle center, but if you move it along this curve, you can see that it also changes the radius of this circle. I'm not going to play around with this as much. We're going to customize the other two curves, but you can keep it actually at 0.5. So you can just keep it at midline, sorry. You can keep it at half. If you right click here, you can choose where you want the evaluation to be. So we can actually just play around with these parameters here. So you can play around with the initial circle radius. You can also play around with where you want the evaluation to be, and you can play around with the second circle, right? So that gives us a lot of customization. So we're going to have a lot of interesting shapes emerging from this. So in the next step, let's keep moving. The goal is actually to find a shape that that encompasses all of these shapes. So one way to do that would be to convert these to polylines, but that might be a bit tricky because how are you going to find these connections here? So you might want to do tangency between these two curves, tangency with this curve, and then you can find this point or another point, but you need to also find where this line intersects with the circle. So that's going to give you a lot of computation. But I'm going to show you a trick to do it a lot faster. So let's first put all of these curves into a container. So I create a curve container. Let's put the last curve, the second curve, and the initial curve using Shift on your keyboard. So we have the 3 curves in a list. Then what I want to do is find some points on these curves. So you can do this in a bunch of ways. You can divide the curves into points. You can also divide them to their length. Let's try divide length. So I'm working with meters, but you can give it any type of threshold. So you can do 0.5. And if I divide the curves into 0.5, you see we get a lot of points. But these points could be used for sampling of the convex hull. Now, what is a convex hull? It is essentially the minimum polygon that contains a cloud of points on a plane, right? So what that means is it basically draws an outline of a shape that goes around these points, and it determines kind of an enclosure for this shape, right? So that can become a lot useful because we essentially have a triangle formed with these 3 circles, but they have different radii, and we want to find the shape that contains these 3 circles. So the convex hull is a native function that is built into Grasshopper. So if you type in here convex hull, you get this type of shape. Compute the planar convex hull for a collection of points. So essentially here we have a bunch of points. And one trick here though is divide length will divide multiple curves into lists. So if you plug this in here, you would actually get convex hull of each circles independently. But we don't want that. We actually want the cumulative computation of the convex hull. So you need to right click here and flatten this list so it becomes a singular list. And now you can see we have actually acquired a polygon shape that contains this initial construction. So if I go here and hide my construction, you can see that this is the polyline that contains the shapes that we had. So if I play with the radius, I can have a lot of different shapes, and I can have rotation for this one as well. I can also control the radius of the third tangential curve or circle as well. But this would be our starting point. So if I'm going to visualize these curves, but you can see that the construction is not perfect because we are sampling some points, right? So we are trying to find the polygon that contains this geometry. So if I were to increase this threshold, we're going to have a lower resolution for the polygon. And that depends actually how you want to move forward. You can also work with less points, less amount of points, or more points depending on how you want to take this exercise. But once we have the convex hull, we have also a bunch of options. So you can also do a fillet, which is you can fillet the sharp corners of a curve, so you can actually turn this into a rounded curve. So let's say we give it some radius value, and the initial polygonal convex hull will be converted to a radius shape or a rounded shape. So you can see that we are actually not getting quite the initial circles, but that's affecting the topology of our shape, right? So however we actually change the default grounded shape, that actually affects how we have computed or rounded up our convex hull polygon. And this will set up the kind of parametric construction for our base. And what we want to do next is to actually work with this curve a bit. So we're going to work with this one, and we're going to find some construction along this shape. So the way I approach this task is basically we can construct some perpendicular planes along this boundary, and these perpendicular planes will have 2 directions. It will have a y direction pointing in some direction, and perpendicular to it we will have an x direction. I'm drawing them by default here. We're going to do this in a bit, but using these planes we can actually construct a lot of custom shapes on this profile. So you can actually, let's say, work with arches. So you can have a bunch of arches along this curve, and we will try to loft these shapes to get the surface defined by these profiles. So that will be essentially the parametric construction of this skateboard landscape. So how do we do that? We have to start by first constructing our perpendicular frames. So let's see, perpendicular frames here. So I give it to my curve, and then we can give it some sampling points. So those could be at any number we want. Now you will see that you have a lot of planes intersecting. So I'm going to reduce the number. You can actually start with 1 to understand what's actually going on. So let's start with actually 2. So when I do 2, these will actually coincide. Let's do actually 3. So these are the 3 curves. You can see the red, or the x-axis, is pointing in this direction. The y-axis is pointing upwards. So x is pointing inwards to the curve, and y is pointing up. So if I were to draft some custom profile, let's say that custom profile is in this shape, like that's an arc, I need to find these points somehow. So my biggest goal will be to find this point that is resting on this plane, and I need to use the plane to find that construction, the location of those points. So one way you can actually do this is using point oriented. So point oriented is located under the vector point command, but it takes a plane as an orientation, and it takes a u and a v value. So the u will stand for the x direction, the v stands for the y direction. So for the profile that I have highlighted, you can see that this point rests in the positive direction of the y-axis, but it rests on the negative direction for our x-axis. So essentially I need to give v some positive value. Let's say it is 3. So it's going to move up, and I need to give it some negative value. So let's say -2 for the u value. So I found that point here. And the next step is to actually find the point on the frame. So you can do this by deconstructing the plane. If you type in deconstruct plane, you get the plane, and you will get some of the vector directions that are on the plane as well. So you not only get the origin, but get the x, y, and z values as well. So the direction we want for the arc is in the negative x direction. So I want to construct the arc using this vector and these 2 points, so that will give me the arc section. So if you go to curve primitive, and there is an arc SED function, which is an arc defined by a start point, end point, and a tangent vector. So that's exactly what we want. So the starting point would be the origin point for our plane. The end point would be this oriented point that we have found. And the direction would be the reversed x vector. So if you plug in x, you would see that the tangent is pointing inward to the curve, so it draws an arc in this fashion. But if you reverse the x vector, so if you type in here reverse vector, now x will point in the opposite direction, and this will give us the arc that we want in the right direction. And you can also make sure that these arches are somewhat like parts of a circle, right? So this is not something I have built in the initial script, but basically you can actually make sure that the x and y coordinates of this point is identical, so that it will define almost like a radius. If these are r, then this point will be resting on a circle, right? So you can actually maintain this by just building kind of a relationship with these 2 parameters. So if you multiply, let's actually try to do this. If I multiply 2 with -1, now this will we don't need this one. This is automated. So I'm just increasing the amplitude for this arc, right? So that's only going to scale up or down. And that's essentially the backbone of our script. So what I need to do is now increase the number of frames. So when I do that, and if I hide the planes, you can see that we have a lot of arcs being formed around this boundary. But of course, we don't have any shape yet. And that's because I actually want to vary these arches a bit. And one way to do that is to use graph mappers. So basically what we can do is create some sort of an undulating shape along this boundary. And we can also customize the type of profiles that we're going to create. So all I have to do is plug in or manipulate this this V value, and we can use a graph mapper. So I'm double clicking here and typing in graph mapper, and we can just start with a linear graph. And a graph mapper is essentially a function that correlates the information we feed in with the graph. So because we have 17 frame calculations, I need a range here, and that range should give me 17 values as well, but we need to actually subtract 1 from this value. So you can do this by right clicking here, creating a quick expression. You can just type in x minus 1, and that will give us 17 values. And when you plug this into the graph, this will act like a percentage. So because we have 17 frames, we can have multiple values being fed to each frame. So I have this graph, I have this number, and this goes into V. So this will basically act like an amplitude for the V parameter, and this will act like, let's see, we have linear, and I can just change, let's say, work with sine summation. So this will give you different height values for these curves. So you can see you can play around with these profiles a lot. But right now they're almost identical. We can actually keep it this way. I have a bunch of different ways of creating this shape. But this will basically customize the profiles that you want to place at each section along the curve. So in the next step, once you have these arches, let's see what we have. We have this filleted curve, and we also have these points. So there are two ways of combining these profiles. You can actually use sweep one. Sweep one will take in, just like the Rhino function, it will take in a rail curve, which is this fillet curve, and it will take in the segments or the sections as the arches. But if you zoom in here, you will see that the geometry is actually not doing a good job of creating these connections, right? So that's kind of messy connections. And we may have to create a second rail to fix this issue. And to create that second rail, we actually have these points available. So you can just do interpolate these points. And initially, interpolation will work openly. So you can see that the beginning and end points, they don't connect. That's because this is not defined as a periodic curve. You need to right click here and set Boolean to be true. So it closes on itself. And now we cannot use rail 1 or sweep 1 because we need a sweep 2. We need a sweep with 2 rail curves. So the first rail curve is our filleted curve that sits at the base. The second one is this curve on top, and our sections are these arches. So that will give us a nicer shape. So this is essentially the geometry, and you can actually play around with a lot of these properties. So you can play around with the graph, you can play around with its amplitude. You can also go back, increase the amount of sections you want to have. You can customize the rounding of the convex hull. You can change the resolution of the computation for the convex hull. You can change this third circle's radii, which will affect how the data is correlated. You can also rotate this shape, change the radius values a lot. So this is basically a parametrically constructed shape now. So that is working around these three circles, and it will give you a lot of options for customization. So one thing I found is that the height value for these, although the X location, let's say we don't want the circles to be parts of a circle, so we can actually do let's say limit the height of these points to be at a certain location. And in order to do that, we can actually not feed in a negative value for the U count, or actually feed in the negative value of this. But let's see, I have actually forgot to connect this one here too. So when I do that, now they become arches. But for the V, we can actually, let's see what V connects. It actually controls the height. So maybe we want the V to be a certain value. So if I plug in 2 here, the height value will be restricted, right? So that will be unitary. So you will only be constraining or controlling the section of these profiles, and you can make it a lot smoother. You can play around with different types of profiles as well for the graph mapper. But one option that we have once all these points are coplanar, you can also offset this one. So if I offset this curve here, you can actually create kind of an offset value, so that can act like a secondary base, right? So we can actually create some offset value, and then using these two, you can create a boundary condition. So you can combine these two. Let's see actually if this would work. Let's plug this in and then plug this in. It actually doesn't like it, so let's see if loft would work. The loft doesn't work as well. It tended to work for the exercise, for the example file I had. Let me check it quickly. This actually worked. I might have to actually flatten it. So let's say boundary surfaces. The reason it doesn't work is because the data here comes in 2 parts. So interpolate curve and offset curve, it gives us 2 different sets of value. So if you right click here and flatten this, that will give you this uniform offsetted shape, this new surface. And I'm also going to take the base and do another boundary there too. So we have this base shape here that we can control with the fillet. I can actually increase the fillet of it a bit. We have this top shape and we have the in-between. So I can just connect all of them using a geometry container. And when we bake it, you would actually get a shape that uses these custom profiles and ends at the same elevation, right? So it starts from the base, has custom profiles, does the sweep, and then we end with the same height value. So that's essentially what this script is all about, but you will have a lot of options to customize it. You can also play around with some of these parameters to see what kind of shapes you can come up with, and that's basically going to be it. So have fun playing with the script. Let's see what you can come up with, and I'll be here next week with a new tutorial for you. And I hope you like this one, and have fun working on this exercise. So I'll see you guys next week. Take care.